My name is Yeju.
And my name is Nariz, and this is our electrochemistry project video.
Do you know what electrochemistry is?
Do you guys know what electrochemistry means?
Yeah, I know a fact.
Electrochemistry is chemistry involving electricity and chemical reactions.
Do you know what a redox reaction means?
Yes!
A redox reaction is when oxidation and reduction take place at the same time. We have the cathode and the anode. In the anode, oxidation takes place, where ions move from anode into the solution. And then at the cathode is where reduction takes place, where ions move from the solution into the cathode. And the electron flow is from the anode to the cathode.
Higher standard reduction potential means it's a stronger oxidizing agent, which means its ability to attract electrons are higher. Cathode should be the one that attracts electron from anode. That's why cathode has higher standard reduction potential. Standard cell potential equation is used when the concentration of cathode and anode are just 1 molarity. There are some times where concentration of the electrodes are not 1 molarity. In that case, we use Arn's equation. In Arn's equation, higher concentration of cathode means higher cell potential. Higher concentration of anode means lower cell potential overall. We're going to put copper strip into copper salt solution and magnesium strip to magnesium salt. And then in voltmeter, the red shows plus, which is the cathode, and black shows negative, which is the anode. And we're going to connect the anode to magnesium strip and cathode to copper strip. Magnesium works as anode and copper works as cathode. This means electrons will be lost from copper and transferred to magnesium, reducing Mg plus ions. We connect the voltmeter because voltmeter value on this will show cell potential of the system. And now we're going to make salt bridge by dipping filter paper into KCl. Make sure that it don't touch your skin or eye because it causes skin and eye irritation upon contact. It shows 0.6. And now we're going to see what changes if we put another salt bridge. And now we're going to see what happened if we switch the side of the cathode and anode. The voltmeter shows negative value. That's a big no.
Result time! And these were the options for half cells provided for us, but we picked these, we chose the strongest oxidizing agent and the strongest reducing agent from the list. Now our results were, when we used 1 salt bridge, the voltage was 0.6, and when we used 2 salt bridges, the voltage was 0.9. And our standard cell potential was 2.71 voltage. Our percentage error was about negative 66.8%, and I think that's because our errors could be the electrode surface oxidized and contamination, but most likely poor salt bridge, because we found out how the voltage increased when extra salt bridge was added. And an improvement we could do is, if at all possible, utilize a U-tube bridge to reduce internal resistance of the salt bridge. Insert a small piece of cotton wool to the U-tube. Clamp the U-tube to the retort stand. The cotton wool acts as a porous barrier, salt bridge, between the 2 arms of the U-tube. It prevents the immediate mixing of the products formed at the anode and the cathode, while still allowing ions to pass through to complete the electrical circuit. Add 1 mKi solution into the U-tube until the level of the solution is within 1 centimeter to 2 centimeters from the top of both ends. Attach the carbon electrode to the alligator clips and insert the carbon electrode into the end of the U-tube. Ensure that the alligator clips are not submerged in solution.
Now we're going to talk about our second lab, which is electrolysis. At anode, the product produced was iodine. On cathode, the product produced was OH minus hydroxide with hydrogen gas. And from the result that we can see at anode, it gives orange-brown color. And on the other hand, it was just clear because it was just water and some Ki ions. And also, it has some bubbles at the end, which means it could be the hydrogen gas. Now we added few drops of starch solution into the YouTube. First, anode shows really dark blue solution, which means that it contains iodine. Starch solution turns blue-black when it's mixed with iodine. On the other side, which is cathode, there was no change. When we add a few drops of universal indicator, anode shows orange-yellow because universal indicator turns orange-yellow when it's less acidic, and iodine, when it's aqueous, it's less acidic. At cathode, there is OH minus produced, which is very alkaline, so universal indicator turns purple. And the result was very accurate because it does follow our hypothesis. And improvements that can be made is that we push the cotton more into the YouTube, maybe in the middle, so that it's very balanced. Because when we put the cotton up, the solution was very concentrated here, and it was said by Mr. Hadi. Now, pour CuSO4 into the beaker. We're using Cu because we're gonna let the electrodes get plated with copper. And we need the solution of the salt in it. Make sure your hand is dry because we're using electricity here. Water is a conductor, guys. Connect copper into plus. As you can see here, a red wire is plus and black wire is negative. So we connect the red one to copper and then black wire to the carbon electrode. Since carbon electrode is at cathode, you're gonna see the electron from the copper to travel and then go to here so that the copper ions in the solution can gain the electron and stick into the cathode. And that's why we call it electroplating, because the copper is getting plated into the electrode. Now we're gonna talk about electroplating results. The beaker at the end was really hot due to resistive heating effect. And due to that, evaporation of the residual water happened. And the water vapors were formed around the beaker. At carbon electrode, the mass increased. And at copper, the mass decreased.
By using Faraday's law, we can find the theoretical mass using current and time from the lab. Percent yield is 100.42 and so on. It's pretty accurate.
Our errors could have been because when the carbon electrode was placed onto a dish after the electroplating, the electroplated copper on the electrode broke off a little, so the mass after the electroplating should have been bigger, but it ended up being smaller. Also, there are small pieces of copper left in the solution that broke off during the experiment. Those pieces were not fully oxidized, so it should have been counted in when we were measuring the total mass after. In Egypt, the shift towards sustainable energy is also creating new opportunities through the application of electrochemistry. Even as traditional fossil fuel employment declines, the country's growing investment in renewable infrastructure such as solar-powered electrolysis plants in the Suez Canal economic zone and plant battery manufacturing facilities is driving demand for skilled workers trained in galvanic and electrolytic systems. For example, local production of lithium-ion batteries and the use of electrolytic cells for hydrogen generation are introducing new technical roles in chemical engineering system design and renewable energy maintenance. These electrochemical developments not only support Egypt's green hydrogen strategy and sustainable energy goals, but also provide a pathway for job creation, helping transition the workforce from traditional energy sector to high-tech, environmentally responsible industries.
Because Korea's electric vehicle growth is producing large amounts of waste batteries, this causes toxic metals like cobalt, nickel, and manganese to leak into the environment when the batteries are not properly disposed of. These leaking metals are harmful because they contaminate soil and underground, damage ecosystems, and can enter the food chain, posing serious health risks to humans. At the same time, Korea depends heavily on imported metals, and these come from regions where mining causes pollution and even child labor. Songil High-Tech addresses this by using electrochemical hydrometallurgy, which applies redox reactions, electric potentials, and ion-selective membranes to dissolve batteries' metals into ions and then recover them through electroplating at high quality.